How are electrons organized around the nucleus of the atom? That's what today's talk is all about, orbital diagrams. So let's talk about first um, the organization that we currently think of, how the electron is organized around the atom. And we have what is called the quantum mechanical model of the atom. Essentially what it says is that the probability of finding of an electron in a location, and that location is called an orbital. When we talk about probability, we're talking about a percentage of the time that we could find an atom in a certain location. And so down here I have a helium atom, and I know it's a helium atom because this pulled out right here is our nucleus. And we have two protons. Let's say these red ones are protons. And we have two neutrons. And if you have two protons, you're definitely helium. And then somewhere around this nucleus are two more electrons. And this density cloud shows the darker the black is in that cloud, the more likelihood you have of finding an electron. So there's a couple of electrons in here relatively close to the nucleus of this atom. Now, we used to think, or it used to be thought, that these orbited around the nucleus much like the Earth orbits around the sun in nice little fixed orbits going around. But we now know it's not the case. Anywhere where you see some gray is a possibility of electrons being located. So they might be found out here. They might be found in really close. But you can see it's darker really close to the nucleus, so they are found there more often. That's what we mean by probability. Okay? And these locations, as we said, are called orbitals, and that's what we're talking about next. So let's talk about some orbitals here. Now we have four different types of orbitals that we're going to be discussing. Each type has a specific shape. Each type has a specific number of electrons that could be located there. Each type has a certain energy, meaning how far or how close from the nucleus these orbitals are. So we're starting with the very first one. It's called an s orbital. S orbital. S orbitals contain a maximum of 2 electrons per s orbital. You can only put 2 in there. They're the lowest energy type orbital, lowest energy, and they also have the shape of a sphere. So that's a three-dimensional sphere, three-dimensional. You can kind of see that they're trying to place it on an XYZ axis. And something else that would be a sphere would be something like a basketball or a volleyball, both spheres in a three-dimensional way. Okay, so that's the s orbital, 2 electrons with a spherical shape, low energy. We next go on to a different type of orbital called a p orbital. P orbitals. P orbitals contain a maximum of 6 electrons. They have greater energy than an s, and they have what we call a dumbbell shape. Dumbbell shape. And this is an example of just one p orbital that could hold 2 electrons. Maybe there'd be one here, maybe one down here zipping around. And then if we were to overlay those, there's actually more p orbitals. We said that we could hold 6, so there might be another one here, and there'd be maybe another one here and back there like that, each holding 1 electron for a total of 6. Okay? So again, p orbitals, 6 electrons. Notice that we're increasing by 4 every single time. We then get to our d orbital. D orbitals have a max of 10 electrons. They are greater energy than s or p, and they have what we call a 4-leaf clover shape for the most part. And so what we're talking about, here's your 4-leaf clover, there's your 4-leaf clover shape in our d orbitals. Okay, with the exception of this one in the middle, not really a 4-leaf clover shape, but for the most part they are 4-leaf clover shape. Again, 4 more to that, 10 electrons. And then now we go on to the highest energy orbital of all of them, and that is our f orbitals with a maximum of 14 electrons. They have a complex shape, and they're the greatest energy orbital. Okay? So let's talk about how we can write orbital diagrams now. Now, here's a periodic table. It's not complete, but there's some stuff on here. And so let's first off do this. Let's break this periodic table into blocks. Let's break it up into our alkali and our alkaline earth metal block. And notice this is 2 elements wide. We call this the S block, because you remember that S's have 2 electrons. So this is our S block. Then we go over here to our nonmetals as well as our semi-metals. and we count 1, 2, 3, 4, 5, 6. This is 6 blocks wide, and so 6, we're going to call this our p block. Because remember, p's contain 6 electrons. Then we go to our transition metals, which are 10 wide, which contain our D block, we call them, and down here in our inner transition metals, 14 wide, we're going to call these guys our F block. Okay, so let's talk about orbital diagrams now. So orbital diagrams are a way to show how electrons are organized around the nucleus. So we use a couple things for orbital diagrams. First, for all 4 of our orbitals, whether they be an S, a P, a D, or an F, we're going to use a box to represent our orbitals. Doesn't matter which one, we're going to label them. For our electrons, we're going to use arrows. Maybe an arrow pointing up, meaning one electron, or an arrow pointing down, meaning another electron. Okay, so let's do some examples here, and we will relate these orbital diagrams to this periodic table that we have here. Okay, so for my first example, I'm just going to do hydrogen. An orbital diagram of hydrogen. Hydrogen, of course, is located up here in period 1. Remember, periods go across like this. It's in period 1, and it has just one electron in a neutral atom of hydrogen. So if we're going to do an orbital diagram, we're going to draw a box because it's in period 1. We call that principal quantum number 1, and we're going to start with our lowest energy orbital, which again, remember, this was our S block here. So hydrogen is right here in our S block. And so we're going to call this first one 1s. And we're going to take this one electron and place it. And that's an orbital diagram for hydrogen. It tells us that hydrogen has one electron in its 1s orbital, and that 1s orbital is a low energy orbital, and it's spherical. That's what it tells us. Let's try helium now. Okay, helium again. And we always start with 1s, by the way. We're always going to start up here at the top. So again, helium is in that first period, principal quantum number 1. And again, we're still in the S block, even though I know helium is across over there, but we're going to use rigid there. We do have helium having 2 electrons. So we're going to put 1 electron in this direction, and we're going to put the other electron in this direction, which brings up a rule. And we're going to talk about the names of these rules here in a little while. But rule number 1 is when placing when we place more than one electron in an orbital, they need to have what we call opposite spins, essentially referring to how they travel around the nucleus. Opposite spins are represented by one arrow pointing up and one arrow pointing down. Okay, so that's why I put one arrow pointing down, representing one electron with one spin, and another electron with a different direction spin. Incorrectly, it would draw this, and some students do this. They'll draw it like this, with both arrows pointing the same way. This isn't the correct way to do it according to this rule. So please don't do that. Okay, so what we're going to do next is we are going to take a look at lithium. Lithium is our next atom on the periodic table. Just going to organize this real quickly here, get our periodic table resized the way it should be. There we go. And so lithium atomic number 3, lithium is. Now, lithium has, because it's atomic number 3, has 3 electrons. And so what we're going to do is we're going to make our first orbital, and then we're going to make our second orbital. And that brings up a rule. Each orbital can have a max of only 2 electrons. And we must fill lower energy orbitals first before going on to higher energy orbitals. So again, we're going to start with our lowest energy orbital, which is our 1s. Okay, and we're going to go ahead and fill that. We're going to put 1 electron in and 1 electron in with opposite spins, as we did with the previous rule. Now, if we go up here to lithium, we can look and see that it is in the second period, and we're still in the s block, so we're going to call this next orbital a 2s. Second period, s block, second principal quantum number 2. So we have 1 more electron to deal with, and so we're going to put 1 more electron in just like that, and there is our orbital diagram for lithium. Now I'm going to let you try an electron diagram for beryllium. So pause the video right now. Boy, that's a terrible square. Pause the video right now and see if you can draw the electron configuration for beryllium, and then we'll come back and press play, and we'll check and make sure you got it right. You did it right? Of course you did. So we have 1s orbital, we have a 2s orbital, we have 4 electrons to take a look at. We're going to put 2 in the 1s orbital and 2 in the 2s orbital, and we're done. Okay? Okay, let's go on. Let's go to boron now. I'm not going to do all of these, but I just wanted to do a few more. Boron. Okay, so boron has 5 electrons in a neutral atom of boron. So we're going to start off the same way we always do, 1s first orbital, then we're going to go to our 2s orbital. Now that would leave us right here at beryllium. Now because we are in period 2, and we're going to go straight across to boron right there, and we get into this block that is 6 elements wide, we're now getting into our p block. P block. So we're going to call this next set of orbitals, and I'm going to put 3 together just like this. We're going to call these 2p. Okay? Now all of these 2p orbitals have the same energy, and that's going to come into play here in a second. And so I'm going to go ahead and start placing electrons. Once again, we have to place electrons in our lowest energy orbitals first. 1, 2 in our 1s, 1, 2 in our 2s, and then we're going to place our last remaining right there in our 2p, and then we are done. That is electron configuration for boron. Now I'm going to skip over to nitrogen. Okay, nitrogen has an atomic number of 7, and so once again, 1s, 2s, and a 2p. Okay, so we're starting off here, and we're going to put 1 electron, 2 electrons, 3 electrons, 4 electrons. Before we get into the p's, remember that I did tell you that these are all the same energy. Okay, we call them px, py, and pz, all the same energy. So we're going to place electrons in the same energy, so that brings us to the last final rule. Again, we'll talk about the names for these rules later. So this rule is when placing electrons in the same energy orbital, place 1 electron in each before pairing electrons. Okay, what does that mean? Okay, so remember, we go back up here, we have 7 electrons to place. We have used 4. There's 1, 2, 3, and 4. So what we're going to do is to place the additional 3 orbitals, we're going to place 1 in the first p, 1 in the second p, and 1 in the third p for a total of 7. That addresses this rule when placing electrons in the same energy orbital, place them 1 each before pairing. If we were to go on to oxygen, oxygen has 1 more electron, we would go ahead and place that electron right here, pointing down. And then if we were to go to fluorine, we'd place it right here, going down. And then if we're going to go to neon, we'd place it right here, pointing down. And then we'd complete all of the 2p orbitals according to the periodic table. And that's